Okay, so this is chapter 3.7, the second video, and we're gonna go over example 4 in this video. We're not gonna finish it because it is algebra heavy, but we are gonna start it so that you can understand how to set up the calculus, okay? So in example 4, you have two posts. One is 12 feet high and one is 28 feet high. They are 30 feet apart. So that means all the way across here, that's going to be 30 feet. They are to be stayed by two wires. So here's the two wires. Here's wire 1 and wire 2. And they are attached to a single stake. So there's a stake here connecting the wires to the ground. And the two wires run from ground level. So there's the ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So should the stake be here? Should the stake be here? We're trying to figure out what will use the least amount of wire. So we're going to let W be the wire length. And so that means that whatever this is, we're going to call that Y, plus Z is going to be the total amount of wire. So this is my primary equation. Let me even use that. This is primary because that's the one we want to maximize or minimize. In this case, minimize because we want the least amount of wire. Okay, so I don't want two variables in my primary equation. I want only one variable so that it will be easier for me to manage. So I'm looking for an equation for y. Well, I happen to know that this is 12, and this I'm going to call x. In fact, they tell me that that's x too. So I can use Pythagorean theorem to find the length of y, okay? So for this particular triangle, let me actually put that in blue again. It's a right triangle by Pythagorean theorem, the secondary equation for that first little wire is going to be 12 squared plus x squared equals y squared. Remember, I'm looking for a way to replace y with another expression. So I'm going to square root both sides. I'm only going to take the positive square root because length cannot be negative. So I'm going to dismiss the negative one. And y equals the square root of 12 squared plus x squared. 12 squared is 144. So that's what y is going to be. So I'm going to be able to substitute for y this entire expression. So now I have w equals square root of 144 plus x squared plus whatever z is. So now let's move on to z. So I'm looking for this length here. So see if you can set up a secondary equation for that on your own. I suggest you pause the video and try that. Okay. So hopefully you notice here that since this entire length is 30, if you name one of them x, the other part is going to be 30 minus x because these two parts have to add up to 30. So if this part is x and this whole thing is 30, then the remainder is going to be 30 minus x. So that means this bottom of this triangle is going to be 30 minus x. This is going to be 28. And I can set up an equation for z. So I'm going to do a secondary equation for z right here. I'm going to erase this to make space for my other secondary equation, my second secondary equation. So you can have more than one secondary equation if needed. So that's going to be 28 squared plus 30 minus x quantity squared equals z squared. I'm going to square root both sides. Again, everything has a positive and a negative square root, but since we're looking at length, the negative square root doesn't matter. So I'm going to not do the negative one. I'm going to get rid of the square sign and because the square root and square cancel each other out. So then z is equal to 28 squared plus quantity 30 minus x squared. So now I can replace z with this entire quantity. So w equals square root of 144 plus x squared plus 28 squared plus 30 minus x squared. So this is now, oops, there we go. So this is now what I want to optimize. In order to optimize this, I'm going to clear some space to work here. Think about what you have to do to set that up, because now I have a primary equation to optimize. All right. So the first thing I'm going to need to do is find. So once I have my primary equation, after I find my primary equation, the next step is going to be to find the derivative of w, which we're not going to do because it's, well, maybe we'll do that part. So we'll find that. So because 144 plus x squared, see if you can do this. Find the derivative of that. So I'll underline this. The next step is going to be find w. I'm going to rewrite this so that the square roots are written as an exponent to the 1/2, because that will make it easier to find the derivative. So the derivative will be 1/2 144 plus x squared to the negative 1/2, because we're thinking of this whole thing as our u. All right, so I'm doing chain rule. So I'm taking the derivative as if this whole thing was one variable. This whole thing counts as one expression. And then I'm going to take the derivative of this expression, which is 2x. Plus, again, I'm going to consider this whole thing one expression, one variable, as if this whole expression were one variable. I'm going to take the derivative of it. So I'm going to take that 1/2 times 28 squared plus 30 minus x quantity squared to the negative 1/2. And then I'm going to take the derivative of this inner part. Well, the derivative of 28 number is just 0, so I don't need to do that part. The derivative of this, I'm going to have to do chain rule again. So I'm going to put times 2 30 minus x, because 30 minus x counts as one variable again to the 1, and then the derivative of 30 minus x, the derivative of 30 is 0, and the derivative of x is negative 1. All right, so then you would have to simplify this and do a lot of algebra to make it look simpler, and that's the part I'm going to stop at. So the next part after you find the derivative is you're going to think about what you would do next. So the next step is going to be you're going to solve for x when the derivative equals 0 and solve for x when the derivative is does not exist. Okay. You're also going to want to find the endpoints of this situation. So the smallest value for x is going to be x equals 0. It can be, so x is this bottom part, so the smallest it can be is 0. The largest it can be, think about it, since these two add up to 30, the longest it can be is 30. So the endpoints are going to be x equals 0 to x equals 30. So I'm not going to bother with any values where x is less than 0 or greater than 30. The next step is I'm going to set up a number line, including x equals 0, x equals 30, and then wherever the derivative equals 0 or does not exist. So the critical numbers, so whatever the critical numbers are. I'm looking for when this is minimized. So I'm going to then plug in w of 0, find out what the answer is for the wire length in that case. W equals whatever this critical number is. W and then plug in this for critical number for X, find the value of W when X equals 30. And whichever of these 4 check marks, assuming that there's 2 critical numbers, which I don't even know because I'm not going to complete the algebra to find out. Whatever is the minimum out of the endpoints and all the critical numbers, that's going to be my minimum wire length. And then that's essentially what they're asking for. They did ask for where should the stake be placed, and so you'll be able to say whatever the answer is for X feet from the shorter pole. Okay. All right, so that was example 4. Example 5 we're going to skip. The biggest part about example 5 is making sure you know that sometimes the endpoints do end up being the maximum or the minimum. Oftentimes, most of the examples we do, it's not the endpoints, it's going to be one of the critical numbers, but it does happen. So you do need to look for the endpoint values if you want to be 100% sure that you got the optimized answer. All right, we're going to do one more example that's similar to example 4 that uses the skill from example 4. And that's going to be number 39. See if you can pause the video, read it, and set it up. It is tricky, so it's okay if you don't get it. But see how far you can get. Okay. There's not a lot of white space here, so we're going to have to do the best we can. An offshore well is 2 kilometers off the coast. So that means that if I draw a coast, I'm going to take advantage of this dotted line. 2 kilometers, the oil well is going to be 2 kilometers going perpendicular to that coast. So this is 2. And this is my oil well. The refinery is 4 kilometers down the coast. So down means in one or other direction of the coast. I'm just going to pick this way. So that means the refinery is somewhere down here. This is 4. Laying down a pipeline in the ocean is twice as expensive as laying it on land. What path should the pipe follow in order to minimize the cost? So here's the refinery. It's on the coast, so it looks like it's not inland. And my pipe is going to look like it's from the ocean. It's going to be part way to land, because if I go all the way there, that is one possibility for the pipe. It's really expensive because laying pipeline in the ocean is really expensive. So we want to put the pipe somewhere to the coast, and then the rest of it will be the remainder here. Okay, so I'm looking to minimize the cost of this pipeline right here. Well, the cost function is going to be in relationship to the length. So whatever this length is under the water, it's going to cost twice as much. I don't know how much it costs per kilometer, but I know that it costs twice as much. So I'm going to let K be the cost per kilometer on land. So that means land, if this is, let's actually call this P1. So pipe 1, pipe 2. So whatever the length of pipe 1 is, that's going to be the land. And whatever the length of pipe 2 is, that's going to be, whatever the length of pipe 1 is, that's going to be on water. And whatever the length of pipe 2 is, that's going to be on land. So the cost of the land one is K dollars, let's say. Let K be the cost. And it doesn't really matter what K is. You can even leave K out, but I'm going to put it here just to be accurate here. So let K equal the cost per kilometer on land of the pipeline. So that means if I have P kilometers of pipeline on land, then that times K is going to be the total cost on land. So this is my land cost of the pipe. Whatever my length of pipe is in the water, it's going to cost twice as much per kilometer. So I'm going to do 2 times K for the cost function times however much pipeline there is. All right, so that's going to be the water cost of the pipe. All right, K is a constant, guys. It does not really count as a variable. It kind of counts as like a fake variable. It's a number that we just don't know. We don't even really care about it because all we want to do is minimize the cost of 2P1 plus P2 or 2KP1 plus KP2. We want this cost to be minimized. And because K is just a number, it's going to end up being not so important. And I'll show you why in a second. All right, so I want the length of P1. I'm going to have to make up a variable here. So this is going to have to be X down here. Okay. So that means the length of P1, I'm going to use Pythagorean theorem. So that's going to be P1 squared equals X squared plus 2 squared. Square root both sides. Again, we're ignoring the negative square root. So then P1 equals the square root of X squared plus 4. So that's what I'm going to replace this P1 with in a minute. All right, P1 equals square root of X squared plus 4. Likewise, I'm going to have to find the length of P2. Well, hold on. This little bit here was X, and this whole thing on the land had to be total of 4. So if X was used up down here, this has to be 4 minus X. So P2 is just purely 4 minus X. That's how long the pipeline on land is. So that means my total cost is going to be 2K times P1, which is square root of X squared plus 4, plus K times P2, which is 4 minus X. So this is now my cost function in terms of only one variable. Remember, the K does not count as a variable. It's just a number that we don't know yet. X is my variable. That's what's going to vary. And I'm going to just erase this down here just to have more space to work with. All right, so this is my cost of my pipeline. Make a little more room here. And so I want to minimize this. So what I'm going to do is I'm going to find the derivative of this. Remember, 2K just counts as a number. And this part here, I'm going to rewrite as 2K times X squared plus 4 to the 1/2 to make it easier to find the derivative of that, plus 4K, because I'm going to distribute that, minus KX. Okay. And then the derivative of this using the chain function again. So I'm thinking of this entire expression as one variable, okay? So first for the chain rule, I'm going to think of this whole thing as like a U. So I'm just going to take the derivative of it as if this entire expression were one variable. I'm going to put that 1/2 in the front. 2K times 1/2 times X squared plus 4 to the negative 1/2. And then I have to find the derivative of this expression that I pretended was one variable. So the derivative of this is going to be 2x plus 0, or just 2x. Plus the derivative of 4k is 0, because that's a constant, minus k. Okay. So I'm going to simplify this a little. 2 times 1/2 cancels out. So the 2x stays on the top. X squared plus 4 to the negative 1/2 means that's actually a x squared plus 4 to the 1/2 on the bottom, minus k.